Okay, so just jumping right into it today, the plan is to continue with factoring to pretty much wrap up this chapter. When we come back next week, we'll probably do kind of just a super quick review of the factoring chapter as a whole, and maybe, wrap up if we have any couple of questions left over from quadratic equations. But we're looking to just finish up the factoring special products section. Uh, we've already talked a bit about general strategy, but maybe just pointing out a couple of points throughout this class, and then discussing that a little more next week, and then mainly talking about quadratic equations. So far we've talked a lot about manipulating quadratic expressions. Well, what if we have two quadratics that are, and of course the thing I selected is not a quadratic, but we talked a lot about manipulating quadratic expressions like this one. But what if we have, say, two expressions that are set equal to one another that are of degree 2? We've talked about how to solve linear equations quite a bit earlier in the course. What about quadratic equations? What's the approach there? We'll see the approach is pretty substantially different than linear equations. Okay, so that is the plan for today. So I want to start by finishing off our discussion of sum or difference of two cubes. And recall that if we have a cubed plus or minus b cubed, this does factor. This is one of our special products. And we know that, for instance, a cubed plus b cubed has a factor of a plus b that can come out. A cubed minus b cubed has a factor of a minus b that can come out. And then what's left over, again, you can kind of memorize what's left over here. A squared minus or plus ab plus b squared. So the coefficient ab has the opposite sign of the, if I can select it, of the b in the previous parentheses. So you can memorize the formula. I think it's, can be a little tough to memorize though, because with all these pluses and minuses floating around, you've got to get them right. The other thing you can do is if you remember what factors out, you can kind of build up the second part from there with a little bit of kind of ingenuity or puzzle solving skills. And we did this one last time, but let's just work through it again. Just as practice, we'll go through these three problems, go through a few problems on the worksheet, and then we'll continue on with quadratic equations. Okay, so x cubed plus 27, I note that this is, well, obviously x cubed is a perfect cube. But I also noticed the 27 is a perfect cube as well. So I have a cubed plus b cubed, where a is x and b is 3. Again, I suppose I could just plug into the formula up here, but let's think through this. We know that the sum of two cubes, the sum of the bases factors out. So I know that x cubed plus 27 is going to be x plus 3 times something. Now, what should I put in there? Well, I know that I need to get an x cubed out. So this x has to hit an x squared in order to make an x cubed. So that's got to be in there. I also know I need to get a 27 out, a 3 cubed. So this 3 has to hit a 3 squared, or it has to hit a 9. And that satisfies the plus 27. This has to be a plus 9 because of the plus 27. The x squared also has to be a positive x squared, because positive x times positive x squared gives me positive x cubed. So, okay, it's looking good now, but I have to be careful, right? My firsts give me the x cubed, my lasts give me the 3 times 9, the 27. If I was just naively looking at this, I might, forget about the outer and inners, but we've had quite a bit of practice. So we remember that there is also the other two pieces I need to distribute to. So I end up with something like a vestigial plus 3x squared plus 9x. So that is extra stuff that is not in the original expression. But if I just left this as it is here, I would have this on the right side. So I don't have it on the left. I would have it on the right. I have to do something to the right side to correct for this. And I noticed that my plus 3x squared comes from multiplying the 3 in the left parentheses with the x squared in the right parentheses. Can I get rid of the 3x squared by multiplying the x in the left parentheses by a middle term, by say a minus 3x? I'm going to try to use different colors here so you can see what's going on. If I put a minus 3x here in this middle term on the right, then the x times the minus 3x gives me a minus 3x squared. That looks good, but I have one more distributive property, the 3 against the minus 3x. Does that work out right? And it does. 3 times minus 3x is minus 9x. And all of this vestigial stuff goes away. And we end up with our perfect sum of two cubes. So I've kind of drawn all over this thing. But I think we can see through all of that this does equal x plus 3 times x squared minus 3x plus 9. We can kind of build that up from basically first principles, as long as we know that for the sum of two cubes, the sum of the bases factors out, and for the difference of two cubes, the difference of the bases factors out. Or, if you'd rather do the rote memorization, just be careful with the signs, which terms always get a plus, and which term the minus sign switches to a positive, or the positive switches to a minus. And then, of course, you can always, if you do the formula and you get an answer, you can always just check carefully. And if something isn't quite working right, you might be able to change a sign somewhere and get it to work right. But personally, honestly, I don't really memorize. I've never really memorized this. I mean, I've taught algebra for a while, so it kind of just like sticks after you've done this for 10 years, but I never made an effort to memorize this. I always memorized this part, remembering what factors out, and then just kind of got the second parentheses the way I did here. Okay, so what about the difference of two cubes? Y cubed minus 216. And here we might not recognize 216 as a cube, but we recognize y as a perfect cube, and we know that we have a special product. Yeah, is there a question? Okay, I know that I have a special product property.
Oh, sorry, my dog just started going off. I don't know why I was unmuted.
No, you're fine. I just wanted to make sure that sometimes people ask questions and
I have quite a few questions, but I'm just gonna listen to you teach for a while, and if it still is blowing past my head as much as it is currently.
Okay, yeah, that works. Yeah, I mean, if you have any questions, I'm happy to answer, or when we jump over to the worksheet, if you want to pop any questions in chat or anything like that, whatever works best for you. Yeah.
I'm just very overwhelmed by all of the numbers and symbols that we're dealing with.
Yeah, it definitely is. Factoring is definitely a step up in difficulty and complexity. And maybe if I had one kind of general piece of advice, it would be, that looking at this kind of, how am I trying to say this? If we saw something like this, like factor this difference of cubes from the very beginning of the course, it would be way too big of a jump to ask, right? But if we think of this as having built on some other factoring material that we've seen, some previous, the previous chapter in chapter 6, operations on polynomials, maybe if we take that perspective, it's a little bit less of a jump and it's a little more approachable. So I think that can sometimes be one of the big factors in math, is just that kind of like anxiety. It's like, oh, there's so much going on here. How am I ever going to sort through it? But we've already done, a lot of difficult stuff, and we've already succeeded at a lot of difficult stuff from the beginning of the course. So I think sometimes taking a step back and, like, in a sense, like looking at how far you've come, and that right now this seems very challenging, but maybe in a week or so, after you've gone through some homework problems and reviewed this section a little bit, maybe this section will be more like, say, solving linear equations or something, that at this point is it's like, oh yeah, we did that before, and it kind of like conquered that beast in a sense. Yeah, but looking at this,
hopefully.
Yeah, looking at this problem, I recognize y cubed obviously as a cube, and I know that I have a difference of 2 terms here. So I might look at this and say, well, maybe I don't immediately recognize 216 as a cube, but maybe it is, right? If it is, it would fit into my difference of 2 cubes pattern. So I can look at 216 over here. And well, I think I'm going to get a factor of 4 out of that, right? This is 200 plus 16. So it'd be 4 times 50 plus 4 times 4. And 54 is actually 2 times 27. This is 8 times 27, or this is 2 cubed times 3 cubed. Or if we think way back to our exponent properties, this is 2 times 3 all cubed. If I have different bases multiplied to the same power, I can, in a sense, factor out the power. It's, in a sense, a distributive property. Or this is 6 cubed. So this does turn out to actually be a cube. I can recognize that. If I don't see it right away, I can recognize it by getting a prime factorization, collecting my prime numbers, and seeing that each factor can be written as a cube. So I do note that this is 6 cubed, and I do have a difference of 2 cubes. So again, this one is harder to recognize than the previous one. We might have recognized 27 as 3 cubed a little more quickly. But here I was suspicious because I saw the 2 terms, the fact that it's a cubic. We did a lot with factoring quadratics, but we haven't talked a whole lot about how to factor cubics. So 2 terms, I have 1 cube, and I say, well, if this was a difference of 2 cubes, this would fit that pattern nicely. So I just check for that, and I see that it does turn out to be the case. And so I know that y cubed minus 216 equals y minus 6. Again, that's the thing that I kind of memorize here, is that when I have a cubed minus b cubed, I know I can factor out an a minus b. What does y have to multiply by to get a y cubed? It has to be a y squared. What does negative 6 have to multiply by to get a negative 6 cubed? That's plus 6 squared, or 36. And then again, I always just come down here and say, okay, I got my y times y squared. That's my y cubed. I got my negative 6 times 36. That's my minus 216. I wouldn't know that off the top of my head, except for the fact that I went through this effort to actually construct that. So I know that that's the case. So this, my kind of firsts and my lasts here, are what give me the thing that I wanted to end up with. But I have kind of an outside and an inside also. So I have a what? Minus 6y squared and plus 36y. So I need to get rid of these. So a minus 6y squared, I need a plus 6y squared to get rid of that. So if I did a plus 6y, that'll run into that y from the y minus 6 and give me a plus 6y squared. And then I'll also have a minus 6 times 6y, which would be a minus 36y. And that does perfectly cancel out all of the extra stuff that I don't want. And this also kind of acts as my check. I know the answer is y minus 6 times y squared plus 6y plus 36. And then lastly, before we do a few problems for practice, something like this. Factor 2 minus 16x cubed. And again, I look at this and it doesn't look like a difference of 2 cubes. 2 isn't a perfect cube. 16 is not a perfect cube, although the x cubed is a little suspicious. But I remember that I usually want to factor out any greatest common factors first. When I factor a greatest common factor first, if nothing else, it's going to make the problem a little easier to deal with. It's going to make the numbers smaller and easier to deal with, but it also will help me recognize some of these special products. And I do realize that there is a factor of 2 in both terms. So that's the first thing I can do. I can say this is 2 times 1 minus 8x cubed. But now I realize that 1 minus 8x cubed is a difference of cubes. 1 is 1 cubed. 8x cubed is 2x all cubed. So for 1 minus 8x cubed, how does that factor? Well, the 2 comes along. 1 cubed minus 2x all cubed. I'm going to get a 1 minus 2x factoring out of that. And then I know that my 1 has to multiply a 1 to get a 1. In some sense, this is like a 1 squared. The blue one is kind of like a 1 squared. I know that a minus 2x has to multiply a plus 4x squared in order to make a minus 8x cubed. And then again, this gives me, my first give me 1 times 1 is that 1. My last give me minus 2x times plus 4x squared is that minus 8x cubed. But my outside gives me plus 4x squared, and my inside gives me minus 2x, and I need to get rid of those pieces. Those are bits that if I just left it as is and didn't put anything else in the second parentheses, I would have an extra plus 4x squared minus 2x on the right-hand side that doesn't appear on the left. So minus 2x multiplied by what gives me a plus 4x squared. That is a or sorry, not a plus 4x squared. I need to get rid of a plus 4x squared. I need a minus 4x squared. So minus 2x against a plus 2x gives me a minus 4x squared. From there, so that gets rid of my extra x squared bit, but then I also have this multiplication here as well. Plus 1 times plus 2x plus 2x, which does perfectly get rid of that one too. And so I see this factors as 2 times 1 minus 2x times 1 plus 2x plus 4x squared. So again, I just take it one step at a time. Is there a greatest common factor? In this case, there was. In the previous two cases, there was not. Is there a greatest common factor I can factor out? Yeah, I can factor out the 2, and then I recognize the difference of the cubes. And then from there, I either, again, if you want to use this formula, if you want to memorize the formula or write it down or use it directly, you're free to do that. You can either use the formula to see that once you get a equals 1, b equals 2x with a minus between them, what should your right hand side look like? Or you can kind of remember what factors out and then just kind of work through it by brute force to figure out what the other factor has to be. Okay, so let's jump over here to the worksheet. We'll work through these 3 problems. Fairly similar to the ones to the 3 that we just did. So we'll take maybe about 5 minutes to work through these 3 problems. We'll come back and discuss them. And then we'll do a little bit of mixed practice for special products, discuss that, and then we'll move on to quadratic equations. So take about 5 minutes for these 3 problems. Okay, it's about 5 minutes, so let's look through these ones. So here we have factor x cubed minus 64. And as I kind of mentioned last class, it might be a good idea to just kind of get familiar with the first few cubes, the first maybe 1 cube through 5 cube or so. And we do recognize that 64 is 4 cubed. So this is a difference of 2 cubes. I know that x minus 4 is going to factor out. What am I going to be left with? Well, x has to multiply x squared to get x cubed. I want to keep that bit. And then minus 4 has to multiply plus 4 squared, or in other words, plus 16, to get my minus 4 cubed. But if I just leave it there, if I didn't put this 4x in the middle, I would then have 2 other terms. I would have a plus 16x minus 4x squared. Those are terms that would show up on the right-hand side, but not in the original polynomial I want to factor. So what does my middle term have to be in the second factor? Well, I need to get rid of a minus 4x squared, so I need a plus 4x squared. So x would have to multiply plus 4x. That gives me a plus 4x squared, and then I check the other distribution. This minus 4 times 4x is minus 16x, and that cancels out the other bit that I wanted to get rid of as well, so that seems like that works. In the second problem, factor 125y cubed plus 27. I note that 125 is 5 cubed, so 5 cubed times y cubed is 5y all cubed. And 27 is 3 cubed. So I have the sum of 2 cubes. I know that the sum of the bases are 5y plus 3 is going to factor out. And down here, instead of doing the kind of reverse engineering method, I just used this formula up here. I noted that a was 5y in this case, and b is 3. So I factor out a, and my cubes are attached by a plus, right? A sum of 2 cubes. So I factor out a 5y plus 3 and a plus b. And the second factor then is a squared, or 5y all squared, or 25y squared. The sign switches, so I had a plus sign in the 5y plus 3. This middle term gets a minus sign. So I have a minus AB, 5y times 3, or that's just 15y. And then plus b squared, plus 3 squared, or plus 9, just coming straight from the formula. And it's a bit quicker to use the formula that way, but I would always prefer to actually check my work at this point. I kind of like internally checked my work up here by like constructing the thing from first principles to work. So I wouldn't feel the need to do an extra check when I go this route, but when I use the formula, I probably want to check my work. So we can distribute it and check that everything works out just right. And then this third problem is maybe a little more challenging. Let me actually move this down just a bit. Bugging me, it's running into the previous problem. But for this third problem, we see, we don't immediately see a sum or difference of 2 cubes because 6 and 48 are not perfect cubes, but this x cubed and this y cubed, along with the fact that there's only 2 terms here, it makes me kind of suspicious that I've got sum of 2 cubes on my radar. I ask, is there a greatest common factor I can factor out? And there is. I can factor a 6 out of both terms. So this leaves me with 6 times x cubed plus 8y cubed. Or in other words, this is x cubed plus 2y cubed. This is the sum of 2 cubes. Now, does it much matter whether I have a variable term and a constant term like up here in previous examples, or whether I have 2 variable terms with different variables? Well, not really, right? Of course, if it was 2 variable terms with the same variable, we would just combined like terms. So, but here we have two different variables, but we still have the same pattern. It's still just the sum of two cubes. It can still factor the same way. I know that I'm going to factor out the sum of the bases, x plus 2y. That's kind of the piece that I memorized, that for the sum of two cubes, the sum of the bases factors out, and the difference of two cubes, the difference of the bases factors out. And then what am I left with over here? Well, x has to multiply what to make an x cubed? That's got to be an x squared. 2y has to multiply what to make 2y all cubed? That's got to be a 2y all squared, or a 4y squared. And just like before, the x times x squared gives me the x cubed. That was, oops, I forgot to bring along my 6. So make sure you bring along your 6. Your factor out in front. Jump the gun there a little bit. But so bring along that 6. My x times x squared gives me the x cubed. That's a piece that I want to keep. My 2y times 4y squared gives me the 8y cubed. That's also a piece that I want to keep. But I get some extra stuff that I don't want. In particular, I get x times 4y squared, or 4x y squared. And I get 2y times x squared, or plus 2x squared y. I'll write it like that. So I need this middle term, this kind of cross term in a sense, to get rid of these. So for instance, how do I get rid of a 4xy squared? I need a minus 4xy squared. So this is going to be going to have to be, and the 4xy squared came from the x times the 4y squared. So I'm going to use this 2y. 2y times what gives me 4xy squared. 2xy. And that's a plus. So x times minus 2xy gives me minus 2x squared y, and 2y times minus 2xy gives me minus 4xy squared. And all of that works just right. It cancels out. In this problem, we have different variables floating around. I think it is just a bit more challenging to do the kind of reverse engineering it, right? We just have a little more complexity going on. This might be an area where using the formula is a little more beneficial. So I think there are pluses and minuses, benefits and trade-offs for both methods. For you memorizing the formula and using it, you have to be really careful with the plus and minus signs, and you have to check your work in an extra step at the end, where the kind of figure it out like a puzzle method, or the brute force method, whatever you want to call it. It's a little more, you're kind of building it up from first principles. You could probably get away with not checking your work at the end because you kind of build it up by construction to be correct. Like basically what we've done here is essentially a step where we check our work. But sometimes whenever you get a more complex problem, it can be a little cumbersome to work with. So like most things in life, right, there are trade-offs. So we can go this path or that path, and there are pluses and minuses either way. Of course, you could take the approach of learn both ways and then use the one that fits best, and that's a nice approach. But obviously that increases the amount of lead time, and it increases the amount of effort that you have to put in to get equally good at two different methods rather than just one. So there are definitely trade-offs, and I would say just focus for now on the method that kind of just hits home the best for you, whether that is memorizing the formula and figuring out what A and B are and plugging in, or whether that's kind of going through this kind of strategic approach and just figuring out what the pieces need to be to make everything work out. So whichever one kind of really makes the most sense to you, I would stick with that. And if you're in the position where you say neither one makes sense to me, which is entirely possible, it's, you know, this isn't trivial stuff. If you're in that position, I would say maybe just stick with memorizing the formula. That's maybe the more quite literally formulaic approach. It's the more kind of straightforward approach. It's the, you know, every problem is going to look more similar under the formula approach than under the kind of strategizing puzzle solving approach. But if you don't like memorizing stuff, then there is another way. And I don't like memorizing stuff. I'm too lazy to memorize things. Okay, so let's look at the next three problems, and this is mixed practice. So we've talked about a couple of different special products in this section. And so far we've said we have this special product and we did a bunch of examples of it, and we have another kind of special product, a bunch of examples. But here we have mixed practice. These are all special products of some sort, but we're not saying which one is which. So the additional level of challenge here is, for each of these three problems, figure out which special product pattern it satisfies, and then apply the right, whether you want to apply a formula or strategy, apply the right formula or strategy to it to get the factorization. So again, take about 5 minutes or so, work on these three problems. And if you forget the formulas, or if you forget what the special product patterns were, there were three of them. There was the perfect square, the difference of two squares, and the sum or difference of cubes. You can look back at last week's notes or last class's notes and get a little more information on those and see what matches up best for each of these three problems. So take about 5 minutes, and then we'll come back and discuss. Okay, it's right around 5 minutes, so let's chat about these. So as I kind of was writing as we're going along here, try to wait long enough that I wouldn't spoil the problems for you, so hopefully I didn't. The first one, well, again, we noticed that it's two terms. This could fit difference of two squares or sum or difference of two cubes. And I look at this and I see a 144 is 12 squared. I might recognize that. That's like the gross or whatever, like that for some reason is, 12 dozen. I don't know why a dozen historically was an important number of things, but it was. And then I noticed the x squared that's making me think maybe this first term is also a perfect square. And 121 is 11 squared. So 121x squared is 11x all squared minus 12 squared. That's a difference of two squares. So I recognize that it fits this pattern. And I know this pattern factors, this pattern, say a squared minus b squared factors as a plus b times a minus b, or a minus b times a plus b. With any of these factorizations, it doesn't matter what order you write them in. So if you wrote your plus first and your minus second, that's fine too. That's equally valid. But we get 11x minus 12 times 11x plus 12. The second one, I see I have three terms. I mean, I guess first off, well, the only special product we talked about with three terms is a perfect square. So that's one hint. But I also noticed that two of the terms are pretty recognizable as perfect squares. 16x squared is 4x all squared. 81y squared is 9y all squared. And so I come over here and I say, I think this looks promising to be a perfect square. But remember, I need one more piece. For a perfect square, I need my three terms, two of which are perfect squares, but that's not quite enough. I also need to check my cross term. I need to check my middle term. In other words, I have like an a squared plus b squared is my cross term plus or minus 2ab. Is it, well, here I know that this would have to be a minus. So is it minus 2 times 4x times 9y? So I compute negative 2ab, and I see that it's negative 72xy, which is indeed our cross term. So this does work out to be a perfect square trinomial. And I know this factors as a plus b all squared, 4x plus 9y all squared. I could FOIL this out, check, and make sure everything works right, and it will. So this was our perfect square trinomial. Again, we were suspicious of that because of the three terms, two of which are perfect squares, but we always have to check that middle term. If this middle term was a minus 71xy or something, well, then it's not a perfect square trinomial. Then we can't factor it this way, and it probably wouldn't factor nicely. And then lastly, 54y cubed plus 2000. We see two terms, and we see a y cube, making us suspicious for something like a sum of two cubes. But it doesn't quite work out. 2000 isn't a perfect cube. 54 is not a perfect cube. But we do maybe notice that there's a factor of 2 in both of these constants that can be factored out. Well, let me start there. I factor the 2 out, 2 times 27y cubed plus 1000. And here I actually see that 27 is a perfect cube. But 27y cubed is 3y all cubed. And I, might not have thought of it, but 1000 actually turns out to be a perfect cube. It's just 10 cubed. So I got to remember to bring along my 2. I don't want to forget that, like I almost did in one of the previous problems. And then my 27y cubed plus 1000. Well, that's 3y all cubed plus 10 cubed. I know that I'm going to factor out a 3y plus 10. This plus being that plus. And then I can either just apply the formula for a equals 3, yb equals 10, or I can use kind of the brute force problem solving approach. I know that I need a 9y squared and a plus 100 to make my cubes work out right. And then to get rid of the extra stuff that's left over, this 90y squared, what would it be? Yeah, plus 90y squared. And then what's the other one? Minus 300y. To get rid of that extra stuff, I need to, or well, that's what I would use to cancel it out. So switch the signs. Like Willy Wonka. Wait, reverse that. But I need my minus 30y in the middle here. I could either apply the formula or go through the brute force approach.
Can you say that for just 2 seconds? I'm sorry.
Oh, no, sorry, what did you say?
If you could just stay there for 2 seconds so I can finish.
Oh, yeah, absolutely. Yeah.
Thank you so, so much. Sorry, my cat was going crazy, so I couldn't do this in a timely manner.
No, you're good. You're fine.
Okay.
Yeah, my dog's going crazy too. I don't know
Oh.
I think it's just one of those days, but I got it. Thank you so much.
The animals
sure.
are
Absolutely.
rebelling.
Yeah, my dog luckily is just kind of curled up and sleeping today. So yeah, but every once in a while he has a crazy day too. So I definitely know how that is.
Yeah, I'm just getting yelled at by my cat like this whole class so far. So
Yeah.
Yeah, my dog was doing that. I had a teacher for my social and abnormal psychology classes that had horses.
Mm.
And one day she had to end class like really abruptly because one of the horses got out. And it was
Oh, wow.
in the window behind her, you could kind of see her like looking back and being like, "Oh, my horse is out. I'm gonna have to leave." And it's like,
Oh, geez.
your horse escaped. Hello?
Yeah. Yeah, it's kind of funny. This whole like remote work switch has, we used to have challenges like, oh, somebody's like, physically like sick, just coughing or whatever. They can't come to class because they don't want to spread everything. And remote work kind of helps us to get around that. But then it brings in new challenges. It's an interesting kind of shift in things. Yeah. Yeah, that's super cool though. I wonder if she I I know there are those like horse farms where like previously abandoned or injured or whatever horses, like they
Yeah.
rehabilitate them and then they use
She
them to
does
help
well,
rehabilitate the kids and
she's a psychiatrist, so
Mhm.
she does when she's not teaching, I believe she said she does work with autistic kids and
Oh
horseback
yeah.
riding
Oh cool.
because
Yeah.
animal therapy is good for autistic kids. So she like that's what the horses are for. They like do animal therapy with
Oh
them.
cool. Yeah.
So I
Yeah,
thought that was
I've
pretty
heard of that
cool.
idea before and yeah. Okay, so let's are there any questions on the special products that we just finished up? So we did a bit of this last time and finished it up today. And then we're going to continue on with quadratic equations. So what's the idea of a quadratic equation? Well, eventually we want to get to is something like this, where we have a quadratic expression, say maybe equals 0, or maybe we have even something like this. Again, this looks a little more complicated, but we're going to work up to this in steps, where we might have like a quadratic equation equaling another quadratic equation or equaling a linear or something like that. But what's the first thing that we can chip away at here? What if we had a situation like this? What if I wanted to solve this for x? So what I might notice here is I have a product of two things. Let's just maybe call them a and b. I have a times b equals 0. And pretty clearly, if x is a real number, then x plus 1 or x plus 2 or a and b are going to be real numbers as well. Well, I have a product of two things being 0. We actually have something in math called the zero product property. And it says if the product of two real numbers equals 0, then either A equals 0 or B equals 0, or both A and B equal 0. At least one of the two factors has to equal 0 in order for their product to be 0. I can't, for instance, take like 1 times -5 and make a 0 out of that. Note that something like this isn't true with, say, addition, like A plus B equals 0. There's lots of solutions to that. 1 plus -1, or 2 plus -2, or 5 plus -5, right? But here we're saying if I have a product of two factors equaling 0, then at least one of the factors has to be 0. We could even generalize this and say if we have a product of, say, n factors, A times B times C, then at least one of the factors has to be 0 for that product to be 0. So we're going to leverage this property here, this zero product property. So if I want to solve for x, what do I mean when I say solve for x? Well, really what I mean is find all values of x for which the equation is true. In other words, find all values of x for which, if you substituted them into the equation, you would end up with a true equation. So I'm not just looking for, a value of x where it's true. I'm looking for all values of x. So if I have x plus 1 times x plus 2 equals 0, then my zero product property says either x plus 1 equals 0. I don't know why I wrote it with parentheses, I guess just so it looks the same as up there. Or x plus 2 equals 0. Either the first factor is 0 or the second factor is 0. But of course, x plus 1 equals 0 says that x equals -1, or x plus 2 equals 0, x equals -2. For quadratic equations, the kind of typical situation is that we get two distinct solutions. We get two real numbers that represent solutions to the equation. I can see pretty clearly that if I plugged in x equals -1, this would give me 0. This would give me 1. 0 times 1 is 0. That works. If I plugged in -2, if I plugged in -2, this bit would give me 0. This bit would give me -1. -1 times 0 is 0. That works as well. I could imagine asking basically the same question in another form. If I multiplied out x plus 1 times x plus 2, I get x squared. My outer gives me 2x, and my inner gives me plus another x, so plus 3x. My last give me plus 2 equals 0. The solutions to this equation are x equals -1 and x equals -2. Why is that? Well, let me try plugging them in. Well, -1 squared is +1. 3 times -1 is -3. Plus 2, 1 plus 2 is 3, minus 3 is indeed 0. Let me try plugging in -2. Does that give me a correct equation? -2 all squared is +4. 3 times -2 is -6, plus 2. 4 plus 2 is 6, minus 6 does equal 0. So typically, I'm going to start with a problem that looks kind of like this. That looks like say maybe quadratic expression equals 0, or at the very least, I'll be able to do some, minor algebraic manipulations to get to this form. So we're really going to start focusing on this form. And we see if we have quadratic expression equals 0, the strategy is not to try to do something like we did in linear equations. And it's a little bit strange. When we think back to linear equations, what was the first thing we did? Well, isolate the variable term. We wanted to get all the variables on one side, all the constants on the other side. We might be tempted to start doing something like x squared plus 3x equals -2. But I don't really know where to go from here because I have two variable terms. I can't, disconnect that x squared and the 3x term. So this actually doesn't get me far at all. This is actually the wrong strategy. For linear equations, it works great. Isolate the variable term, isolate the variable, simplify, works great. For quadratic equations, because we have two fundamentally different variable terms, two unlike variable terms, we have to take a different approach. There are a couple of different approaches to solve quadratic equations, and we're going to cover one in this course, and the other approach is covered in MAT090. So it's a slightly more advanced approach. The approach that we're going to cover doesn't solve every quadratic equation, but it solves the ones that work nicely enough. So just as a caveat, when we go through and we work on solving quadratic equations, some of them will just say we're not able to solve them. That's not necessarily saying that no solution exists, that there is no value x that satisfies that equation. That's not exactly what we're saying. We're just saying that this first technique that we're learning doesn't get us the solution. It could be that there's no solution, there's no value x that solves the equation. For instance, x squared equals -1 would be a good example of that. Any real number we put in for x, when we square it, it turns out to be positive or maybe 0, but never negative. X squared can never be -1 when x is a real number. So we could have a setup like this, or we could have a situation where just the method that we're talking about doesn't happen to work here, and we need a slightly more advanced method that'll be covered in a future course. So just a little caveat there. But what is my strategy for this course? What is my kind of relatively speaking simpler strategy? My strategy is to take an equation like this, get all of my quadratic bits on one side, get everything on one side, all of my variables as well as my constant, and then try to factor so that it looks like that. Right? I try to factor to get to a form like this where I have products of linear factors equaling 0. If I have a product of two linear factors equals 0, then either the first linear factor equals 0 or the second linear factor equals 0. I've taken my quadratic equation that's quite complex, quite difficult. I've broken it into two equations, into two problems, but each problem is easier. Each problem is just a linear equation. And then I can just solve each linear equation. These two happen to be pretty easy to solve, but I solve each linear equation and get my two solutions. And then I would say something like, the solutions to this equation are x equals -1 and x equals -2. Or if I wanted to be really pedantic about things, I might say something like the solution set is -1, -2, something like this. In my opinion, I don't use solution set notation. Some folks make a big deal about it and some folks use it. So, it's possible that in your MAT080 class or in high school, or maybe even in our 108, depending on which instructor you take, they might like this solution set notation. I think it's a lot of superfluous stuff and syntax and ideas and all of that. So I would just say something like the solutions to the equation are x equals -1 and x equals -2, and I would leave it at that. So let's work through a few examples. Let's take this for example, x squared plus 8x plus 7 equals 0. Let me zoom in just a little bit here, make it easier for you to see. So x squared plus 8x plus 7 equals 0. Again, what I don't want to do here is start doing the linear equation approach where I try to isolate variable terms. I don't want to put the 7 on the right-hand side because then what the heck do I do with x squared plus 8x? I'm not sure. What I want to do is get all of my stuff on the same side, which it already is. That's great. And then I want to factor. And I might realize that this factors as x plus 7 times x plus 1. I'm not going to go through, always go through all the factoring details here. But I would recommend that for the ones that I don't go over, like this one, go through them in your notes, fill in that gap in your notes, and see why does it factor this way. But here I have a product of two linears equaling 0. I apply my zero product property and say either x plus 7 equals 0 or x plus 1 equals 0. That is a 7. Or in other words, x equals -7 or x equals -1. These are my two solutions. I can plug in up above, -1 squared is +1, plus 7 is 8, and then 8 times -1 is -8, so 8 minus 8 is 0, that does work. -7 squared is +49, plus 7 is +56. 8 times 7 is 56 as well, but with a 8 times -7 is 56 with a negative. -56 plus 56 is 0, so that works as well. So my two solutions are -7 and -1. If I have a problem like this, x squared plus 14x equals -13, the first thing I want to do is get everything on one side. So the first thing I do is put the -13 on the other side. Right? I do that by put -13 on the other side, I mean add 13 to both sides. Just to be very clear what I mean by that. I get x squared plus 14x plus 13 equals 0. This factors as x plus 13 times x plus 1 equals 0. And again, now I have the product of two factors equals 0. So that tells me either the first factor is 0 or the second factor is 0. Or in other words, x equals -13 or x equals -1. Something similar here, x squared plus 100 equals -101x. I want to get everything on the left-hand side, so I add 101x to both sides. And now I factor on the left-hand side. I don't want to try to start factoring this or start factoring this, right? Because if I were to start factoring and then move another term over, that's going to mess up my previous factorization. I need a product equaling 0, not like a product plus some other thing equals 0 or something. So I move everything over to the one side. Now I can factor. This is going to factor into x, x plus 100 times x plus 1 equals 0. And again, a product of two factors equals 0. Either the first is 0 or the second is 0. Or we say x equals negative 100 or x equals negative 1. So these were more straightforward problems to factor. The factoring wasn't super difficult in these three, but we're just introducing the idea of the zero product property, the general strategy. So let's take a look at these three problems. Maybe take about 3-4 minutes or so to go through these, and then we'll come back and discuss them. So work through these problems, practice them. Remember, get everything on the left side, factor, use the zero product property, and get the solution. So we'll come back in maybe about 4 minutes or so for this one. Okay, it's just about 4 minutes. Let's look at these ones. So for x squared plus 8x plus 15 equals 0, we see everything is already on the left side, so we're ready to start factoring. We note that 5 times 3 is 15 and 5 plus 3 is 8. So this factors in x plus 5 times x plus 3 equals 0. And now we have a product of two factors equaling 0. So either the first factor is 0, x plus 5 equals 0, or the second factor is 0, x plus 3 equals 0. And solving each of those independently, we see x is -5 or x is -3. These are our two solutions for this equation. And if we wanted to, we could plug both of these back in and see that they do indeed yield a correct equation. For the second and third problems, we had to do a little bit of work before we started factoring. So we need to get everything on one side. So here, this minus 18 that's on the right side of the equation, I add 18 to both sides to get x squared plus 11x plus 18 equals 0. And now I look at that left side and I see how it factors. I notice that 9 times 2 gives me 18 and 9 plus 2 gives me 11. Remember, that's the strategy for factoring trinomials where the coefficient of x squared is 1. So this gives me x plus 9 times x plus 2 equals 0. Again, product of two factors equals 0 means one factor equals 0 or the other does. X plus 9 equals 0 or x plus 2 equals 0. So x equals -9 or x equals -2. Again, these are our two solutions to this equation. If we plugged either -9 or -2 in to the left-hand side, we would get -18 and match the right-hand side. And then lastly, y squared plus 60 equals -19y. Similar to above, we want to first get this -19y on the other side as a plus 19y. So we get y squared plus 19y plus 60 equals 0. Right, it's super important to get the 0 on the right-hand side, otherwise we couldn't use the zero product property. But we do that, and I'm looking for two numbers that multiply to 60 that add to 19. This one's a little more challenging, but it turns out to be 15 and 4. So this quadratic on the left factors to y plus 15 times y plus 4 equals 0. And again, we have the product of two factors equals 0. So one of the two has to be 0, either y plus 15 equals 0 or y plus 4 equals 0, giving me my two solutions, y equals -15 or y equals -4. So I think we can really see that solving quadratic equations, it's really almost all stuff that we've done before. It's either things like just moving terms from one side to the other, or factoring, or solving linear equations. Really, the only new thing here is going from here to here. It's understanding why we need a 0 on the right-hand side, or whichever side we decide to put the 0 on, so we can use the zero product property, and then factoring and using the zero product property. So we need to set ourselves up to use the zero product property, and then we need to use it. So these kind of two steps, really this step, really this one here, but the kind of setup to this is to get a 0 on one side. Getting a 0 on one side, factoring and using the zero product property, those are really the new ideas in this section. Everything else we're leaning on is old work, right? Is factoring, we've done that before. Solving linear equations, we've done that before. And then, of course, just things like moving terms around from one side to the other side of an equation, we've also done that kind of work before. So really the new idea is this zero product property, and that's really what we're leveraging to solve these quadratic equations. Again, it looks very complicated and complex. There are a lot of steps to it. There's a lot of moving pieces. But if we remember the general strategy, get a 0 on one side, factor and use the zero product property. Most of the surrounding work is stuff that we're already pretty comfortable with. Okay, let's look at a few more examples. So y squared minus 5y equals 7. And again, we remember our general strategy. We need to get a 0 on one side, factor, use the zero product property. So this 7 has to go on the other side. Y squared minus 5y minus 7 equals 0. And now the factoring is a little more difficult because I have some minus signs involved, but I'm looking for two numbers that multiply to -7 that add to -5. So if I think of like m and n, I have 1 and 7, but they have to be opposite signs, +1, -7, or -1 and +7. And m plus n equals -5. There's actually no solutions to this. This is prime. What does it mean if I get a quadratic that's prime? Well, all that it means is that I can't solve this equation this way. It could be that this equation doesn't have a solution. That's a possibility. It could also be that this equation has a solution, but this method doesn't solve it, and I would need the more advanced method that we cover in the next course. So either of those possibilities are true, but for our purposes, we'll just kind of write a question mark. We're saying at this point, there's no way to solve this using the technique that we're talking about. That's not to say that there's no solution, that there is no real number y that I could plug in here and get a correct equation. There might be, but if there is, I can't find it using this method. What about a very similar looking problem, y squared minus 5y equals 6, or y squared minus 5y minus 6 equals 0? Are there two numbers that multiply to -6 and then add to -5? Yeah, I think that's -6 and +1. So my lasts multiply to give me -6, and my outside plus y, inside minus 6y, that gives me -5y, so that looks right. I use my zero product property, either y minus 6 equals 0, or y plus 1 equals 0, either y equals 6, or y equals -1. So two very similar looking problems. The only difference was this number on the right-hand side. One we could solve, one we at least weren't able to solve with our methods. And then what about this one? X squared minus 2x minus 8. So I'm looking for equals 0. So we're already set up to go. I'm looking for two numbers, m and n, that multiply to -8. So that could be like 1 times 8 or 2 times 4. They need to multiply to -8, and they need to sum to a negative number. So the negative has to go on the bigger number. Do any of these add to -2? Yeah, this looks like the right choice there. So I get x plus 2 times x minus 4 equals 0. Let me check that. First, give me x squared. Last, 2 times -4 is -8. My outside is -4x. My inside plus 2x, that is -2x, so that looks good. I have the product of two things equals 0. So again, I apply my zero product property. X plus 2 equals 0, or x minus 4 equals 0. X equals negative 2, or x equals 4. Those are my two solutions. So we can see the factoring is getting a little bit more challenging now. But the strategy for solving the quadratic equation is the same. I get stuff equals 0, do whatever I need to do to get into that form. I factor if I can. If I can't factor, I just say, okay, I can't solve this equation with this problem. Maybe there's no solution. Maybe there is a solution, but I just can't find it with this strategy. But if I can factor, then I use my zero product property and solve the resulting linear equations. Okay, so take a look at these two problems. And we'll take maybe 3 minutes for these two problems. So work through these two. We'll come back in a few minutes and go through the answers. Okay, so for these problems, we ended up actually having two problems that were both prime. So we had two problems that we ended up with a quadratic that we couldn't factor nicely. We weren't able to find solutions. Maybe for this second one, kind of an interesting question is, what change could I make to this problem to make it solvable with this method? So it's kind of an exercise. What could you change? in the problem to make it solvable. And this, and
The
this,
perfect square thing?
sorry.
Is this the perfect square thing or no?
I suppose we could make it a +4. So yeah, if we had, say, something like x squared plus 4x plus 4 equals 0, that problem would be solved. That problem would be solvable. This would indeed be a perfect square. The perfect square is actually a special case we're going to talk about next time when we wrap up this this topic. But yeah, this would be a perfect square. This would be x plus 2 all squared equals 0. And then this might look a little strange to us. We're not used to seeing this pattern. Again, we'll discuss this a little more next time, but yeah, so turning it into a perfect square would make it solvable. Or really just changing this 4 to say something like maybe 19 or maybe 11 or 9. Or even if I wanted m plus n to be a negative number, these both could be negative and still multiply to a positive 18. So I could have, m plus n, or the middle term here, be, say, negative 19 or negative 11 or negative 9. So these are some things you can do on your own when you go back through your notes with math classes, or with, kind of like physics, or maybe to some extent something like chemistry. Or you can kind of ask yourself, okay, what if something changed, right? Or how could I change the problem to make the solution come out in some sense like fundamentally differently? So these are some kind of follow-up questions you can always ask yourself. A lot of times students ask, like, how can I study for an exam, or how can I get a deeper understanding of the material? I think this is a great way to do it, is to go through problems that you've done in class and say, for this one, let's say, or for the one that we did in the lecture portion, for both of those, we ended up with prime polynomials, and we just said, okay, using this method, we can't solve this. But like, if you were the teacher and you said, okay, I mean, I pulled this one out of a book and it's prime, I can't solve it, but I want to show the students an example that I can solve, what would I have to change here? How would I change this, and in what way, to come up with a different problem that I would be able to solve? What would that look like? And I think this kind of just playing around almost with these problems, with these ideas, is what really gets a deeper understanding for some folks. Okay, we've got a few minutes left. So let's take maybe one of these problems from the lecture side and one problem from the worksheet side, and then we'll leave the last couple for next time, along with some of the special cases like the perfect square example that we'll talk about next time as well. So a problem like 4x squared minus 5x plus 1 equals 0. This is already set up pretty nicely for us. We got everything on the left side. We're already set up to factor and then use that zero product property. So this one, I could use AC grouping, I suppose, but this also seems pretty straightforward. Like 4, there's not that many ways to break up 4, and 1 just has to be 1 times 1. So I know I've got to have 1 and 1 there, and I know they've got to both be the same sign. If I have something like 2x and 2x, say minus 1 and minus 1, well, my first give me 4x squared, my last give me plus 1, but my inside plus outside gives me minus 4x, not minus 5x. So that doesn't seem to quite work. But if I did 4x and x, that's a 4, not a 9, with minuses in between. Now again, my first give me 4x squared, my last give me plus 1, my cross terms give me minus 4x minus x minus 5x. That's good. I can use a guess and check, or I could use AC grouping. I have a product of two things equaling 0. Either the first is 0 or the second is 0. So either x equals 1 or, and now I have a little more of a legitimate linear equation to solve, right? I have to do a couple of equation solving steps. Maybe I'll come off to the side. Now I have a linear equation. Now I want to do my linear equation solving steps. I want to isolate the variable term, isolate the variable, simplify. I isolate the variable term by adding 1 to both sides. I isolate the variable term by dividing by 4. And I can't really simplify any further, so x equals 1/4. So even these more complicated scenarios where my coefficient of x squared is not 1, the only thing that really that really changes is we end up with linear equations that might be just a little bit difficult to solve, a little more difficult to solve, right? We might have to come off to the side and do a little bit of scratch work, but still fundamentally the same. Okay, let's look at this example. Take about 2 minutes or so, and I'll start in on it in a minute or so, but take about 2 minutes, try to work through it, and we'll come back in a couple minutes and wrap it up. Okay, so this one, again, I just use the guess and check method here. I know that for 5x squared, I have to have one factor that has a 5x and the other has to have an x. Because 5 is prime, that's the only way it breaks up, is the 5 times 1. 11 is also prime, so it's got to be 11 times 1. So I either need the 11 with the 5x and the 1 with the x, or vice versa. I know that if I have the 11 with the x, the outside is the 11 is going to hit the 5 and make a 55x. That's going to be way too big. That's not going to work. So it's got to be the other way around. And I check, my cross terms are indeed plus 5x plus 11x plus 16x. Looks great. My zero product property means that either 5x plus 11 equals 0 or x plus 1 equals 0. X plus 1 equals 0 is easy to solve. X equals -1. 5x plus 11 equals 0. Well, we just come over here and do a couple of linear equation solving steps, and we get x equals -11/5, giving us our two solutions of the quadratic equation, -11/5 and -1.